All right, so as I said, on Axis, you can see the test is now next Friday instead of next Wednesday, and the lab report's due the following Monday. We're going to go over together today, review together worksheet 1, since that is what was due today. You're supposed to be finishing that up. We're going to take a short bit of notes on vertical uniform circular motion that will kind of directly branch off from worksheet 1. And then we're going to have a brief discussion on the lab, just a couple of comments, and then you're going to have probably a half an hour or so to work with your lab groups to either work on the lab report, getting your graphs done, getting your data analyzed, or working on worksheet 3, which I want you won't necessarily have to have it all done on Monday, because we're not going to be able to get through all of it Monday since there's so many other things, but I do want you to at least try to get a page or two of that done for Monday, because that's going to be a big part of our review for the test. So that's what you should be thinking about for the agenda today, and also how to prepare over the weekend for next week. So test Friday instead of Wednesday. All right, any questions about the schedule changes? It's all adjusted on Axis already, but okay. So for worksheet 1, I asked you to try to finish it up, so hopefully you have that done and you can follow along and get questions answered. This is a great study guide for the test. Most of these worksheets that we're going to be going over, this one and the one on Monday, we might do a third one on Tuesday, or at least part of one. They're all geared towards giving you practice problems to prep for the test. So I've had a few lab assignments already, a few homework assignments already, so I don't think we need to necessarily just grade it, and I'd like you to keep it in hand so you can use it to review. So I'm not going to collect this one, but these kinds of questions are very similar to what you're going to see on the test. I just finished making the test last night. I'm just doing final edits on it, and so I know that several of the things we're going to talk about today, both from this worksheet and from your lab, and things we're going to be looking at in the notes, are very much on your test next week. So try to pay good attention, get your questions answered, make sure you understand it really well. So for number 3, it says we have a car entering a circular turn at constant speed. If it's moving at a constant speed, can it still be accelerating?
Yes.
Yeah, in this case, would it be accelerating?
Yes.
And why is that? Changing direction, good. So make sure you're very clear on that so you don't miss that part of the test. That shows up. And then it says, name the force and interaction between objects that allows the car to travel in a circle. In what direction does the force push on the car? Draw a force diagram. And from this Arizona State curriculum, they always call them force diagrams, but College Board will always refer to it as a free body diagram. They are technically two different things. Free body diagrams have specific details, like you have to have a dot, you have to have all arrows radiating out from that single dot. A force diagram is more flexible, where you could just draw all the force vectors on an actual image of the object or whatever, trying to figure out torque moments and things like that. So a couple different approaches, but College Board always asks for free body diagrams like what you see here. And then it says we're thinking about the car approaching head on. So the circle is like a top view, and then the free body diagram is a side view. So if this is the car traveling in a circle and the triangle is where the car's at and the direction it's going, you're standing over here somewhere. It's coming right at you, but it's turning, so it's not going to hit you, hopefully. Right? That's the plan. And then thinking about what the free body diagram looks like as you're looking at the grill of the car, its weight would be straight down to the center of the earth because of the earth's gravitational force field. And then the ground is lifting with an equal but opposite normal force. So that means the car is not rising or falling vertically. And the friction between the tires and the road provides a net force allowing the car to turn. If there was no friction, it couldn't turn. That's why when you hit ice, when you hydroplane, when you hit a slick spot, if any of you have ever experienced it before, you're trying to turn and the car just keeps going straight until it regains traction. And so the friction actually allows it to turn. Without the friction, it couldn't. And so what's true about the two vertical forces in this free body diagram? They're equal and opposite, right? Equal in magnitude, opposite direction. So another way to say that is they're balanced, right? Balanced forces. So there is no net force vertically, But is there anything to balance the friction force? Nope, that means the friction force is the net force, right? The leftover, what doesn't get canceled or balanced, is what we call the net force. And is this net force centripetal in nature? Is it causing circular motion? Sarah will be nodding, yes. Therefore, this net force of friction is the centripetal force. All right. Part B, describe the motion of the car if that force, the friction, suddenly vanished. So if the car was coming around the circle like that and you were standing in front of it and all of a sudden it quit having friction, if it hit ice or something, it would be skidding straight towards you, right? Hopefully it gains traction before it hits you or you dive out of the way, but it would be coming straight towards you based on the scenario they've described here. It would go tangent to the circle. All right, any questions on parts A or B? The kind of qualitative, concept-based questions? Yeah, Griffin?
Why is it static friction and not kinetic friction?
Great question. So yeah, it seems kinetic because the car is moving, but here's what's happening. See if I can illustrate with my hand on the board here. So if this is the road, if I just draw like a curved road, the car is going like this along the curve, right? And so if it skids, it's going to go this way, right? So the friction is actually not letting the tires skid against the road. So the car has kinetic energy, but the surfaces that we're worried about right now are the tire surface not letting the car go sideways based on the curve, right? So if it's going around the curve, if it starts to slide, it's going to go this way. And if there is friction, the friction is keeping it from sliding. And so we call kinetic friction sliding friction. So there is a rolling friction of the car going forward between the tires and the road, but it's not sliding, it's not skidding, and so that's static in nature that's keeping it going in a circle.
Okay.
So there's multiple kinds of friction going on in this scenario, but it's a static friction that makes it go in a circle because it's not skidding. Now, if you were going too fast and your tires started to skid across the road, then it would be kinetic. And that's why it's hard to recover when you lose control, because the coefficient of kinetic friction is almost always lower. So now not only are you skidding, your coefficient of friction dropped even more, so to stop skidding is going to be even more complicated or more difficult until you slow down enough. Did you have a question, Quinn, or comment? Okay. Any other questions about this scenario? All right. So now let's look at the math. Part C says, well, what if we have a 35-meter radius turn? It's level, so there's no embankment to it. It's just a flat turn. If the car has a mass of 1,200 kilograms and the coefficient of friction between the tires and the road is 0.85, what is the maximum speed that a car can travel through the turn? So we talked about this last week or earlier this week, how this is how civil engineers working on the highway department would try to figure out what signposts to put on a curve on a road. Well, now we're actually doing the math instead of just talking about it conceptually. So I'm going to actually show you over here. It's pretty much what's on the same as what's on the screen, but I have just slightly different. I don't know. Hopefully you can see it on the video. If we go back to the free body diagram, we can see that the net force is the friction force, right? And that it is the only force causing this to go in a circle. So the net force is the friction force, and it's also the centripetal force. So what they wrote on the screen is perfectly fine. I don't have any complaints about it at all. I just wanted to show you how my brain would process this in case it's helpful if what they show is maybe not making as much sense. I know the net force in this problem is centripetal because it's making the car go in a circle. And I know that friction is actually the kind of force that's making this, because centripetal force has a generic equation, but centripetal force is a generic term. There's always some other force causing it. Tension, gravity, in this case, friction. It has to be some other force. So we're always going to say that centripetal force, generically speaking, can be calculated this way, but specifically there's always going to be something else causing it. There's some other kind of force, because this is just a generic term. So in this case, it is friction. So then I can say, well, I know net force is always m times a, but seldom do I ever actually use that formula in these problems. since the net force is centripetal in nature, I can substitute A for the v squared over r, because the acceleration that's centripetal is v squared over r. And since it's caused by friction, I can substitute in mu times the normal force, because that's the equation for friction. So it's just subtle differences. There's not much different from what they have here on the screen. The main thing is that I like to notice or notate that it is a centripetal force, because then that reminds me that I can use this equation. Okay, so they've kind of just done it without ever really saying in any way that it's centripetal. So sometimes that confuses students. They're like, wait, it's centripetal force. Why doesn't anything in here say centripetal? And you don't have to. You could do it like they do it. You could do it like this. They end up getting in the same place. It's just this is how my brain processes. So if that helps you in any way, great. If what you see on the screen from what they do makes more sense to you, also great. Whatever works best for you. It's in the end almost the same, just subtle differences. So you can see on their version, the net force is friction force, which is, almost the same. Then they write the equation for friction force, which I did as well. And then they go the step further, which I didn't do, because beyond that, then my work would be identical to theirs. So there's not really any reason to change it. Why did they change normal force to mg? Aaron?
Cancel the mass.
Yeah, so it will cancel the mass mathematically, but when I look up here, these two are equivalent. So since this is mg and these are equal, the normal force is also equal to mg. And that does allow us to cancel the masses out algebraically down here. So we substitute normal force with mg because normal force is equal to the weight in this scenario. Then in the second row, you can see they are canceling out the m's, and then they're isolating the v. So they multiply both sides by r, they cancel out the m's, or you could say they divide both sides by m, and then they square root both sides. So they end up having v is equal to the square root of the coefficient of friction, which was given in the question, times g, which is constant 9.8, times the radius, which was also given in the question, 35-meter radius. And then we can just substitute in. So does the car's mass even matter? That's why they don't care if it's an 18-wheeler. Now there's other issues, like the 18-wheeler might be top heavy, could tip, but in terms of the friction necessary to keep the cars on the road, they don't care if it's a tiny little electric car or a big old SUV or whatever. It doesn't matter. The mass doesn't matter. And so that 17 meters per second, what that means is, as long as the car doesn't go faster than 17 meters per second, it's going to have enough friction to make the turn. Remember when we first learned about static friction, we saw in the equation it was less than or equal to, right? So if they're going less than 17, there's still enough friction. If they go 10, 15, 16, it's all good. 17, they're right at that breaking point. 17.1, now they're going to start sliding. And then it's kinetic friction, because now the tires are sliding against the road instead of gripping the road. And as they start sliding now, the coefficient of friction changes and it's harder to recover. So any questions about the math behind this scenario? Anything about the steps or the numbers or anything at all? All right. Number 4, the International Space Station orbits Earth once every 90 minutes. Name the force that allows the ISS to orbit Earth. Well, hopefully that wasn't too difficult to think through. It's just gravity that holds the space station in orbit. And then explain why the space station does not crash to Earth because of this. Like, why doesn't it just free fall down to Earth? And the concept is that when they launch the satellite into orbit, they don't just shoot it straight up and hope. Like, they launch it with horizontal velocity. So it goes up at an angle, and then when it reaches its orbit, it actually has horizontal velocity. So it's a projectile. It's like similar to when you roll a ball off a table. It has horizontal velocity and vertical acceleration. The difference between a ball rolling off a table, when the ball rolls off the table, what direction does the acceleration due to gravity point? So Straight down. And does it change during the flight of the ball? It's always straight down. When something's far from the surface of the Earth in orbit, at this point, like if this is the Earth, at this point, gravity is straight down, but then when they're here, now it's at this angle. And when they're here, now it's at this angle. It is always still to the center of the Earth, but that angle of that force keeps changing. So it starts off like a parabola, like this ball rolling off the table. So it's launched in a parabola, but then as it's going along this parabola, the angle of that gravitational force changes, so that changes the shape of the parabola. And then here it changes a little more, it changes the shape of the parabola. And eventually, that parabola deforms into a near circle, because it just keeps changing, because the direction of the gravity keeps changing. All right? So it's like a projectile, like you launch off a table. It's just that it's so far from the Earth, the angle of that gravitational force field isn't just straight down because it's moving around. And so it just keeps missing the Earth. Now, if it slowed down, if it wasn't going fast enough, it would start to spiral closer and closer and closer and closer, and then it would come crashing down. So it has to have enough velocity to keep it in that orbit. Questions about number 4? All right, I want to highlight, like we did here with the centripetal force, I want to highlight, hopefully it'll let me draw on here. Sometimes it works. If this had asked some math questions, this is how I would process it again. What is the net force in this space station problem? What's causing the net force? Gravity. Is it centripetal in nature? Yes. Okay. So I could say the net force is centripetal in this problem, and it is also gravitational that's causing that centripetal force. I know those 3 things are equal, right? And net force just generically is m times a, which probably isn't that helpful, but we can make a note of it. What's centripetal force's equation? Yeah, m times v squared over r. The a becomes v squared over r. So m times v squared over r. What is the equation for gravity? Well, if we're just talking about relative to the Earth, but
it's g, lowercase g.
that would only be an object that's close to the surface of the Earth.
It's
like
like
big
the
G,
M1,
M1,
M2.
Yeah.
Oh, big G.
Yeah, because what you're describing would just be the weight of the object close to the Earth, but now we're talking about something out in space. So it would be G M1 M2 over R squared, right? That's going to be the gravitational force between the satellite and the Earth, because now it's not just an object's weight that we need to worry about. We're talking about the gravitational force that exists between them to keep it in orbit. And then we could go further. We could say, well, I probably don't need to worry about this because this is kind of almost too generic, but that's a nice relationship, right? I can see that I've got the object's mass here is going to cancel. Whether I call it mass 1 or mass 2, I just pick one. One of them's the object and one of them's the planet, right? So that's going to cancel. R is going to simplify. If I multiply both sides by R, it cancels on this side and simplifies over there. And now I know that v squared equals the gravitational constant capital G times the mass of the Earth divided by the distance between the Earth and the satellite. And so if I needed to know, hey, how fast should this satellite be going so that it doesn't spiral down and crash into the Earth, that's my equation. And I just square root both sides. And I get v equals square root of big G, mass of the Earth, over R. So similar to the car problem, here I'm just thinking about how fast does this satellite need to be moving in order to not crash down. I'm mainly going over this just so you can see another example of how you can process these kind of problems, and also because I know there's a question like that on your test next week. So I want to make sure you're understanding how to think through some of these things. Anything you want to ask before we move on? All right, I added that because this worksheet doesn't ask it, but you need to think through it, so I'm giving you a preview, a little sneak spoiler for your test. All right. The last page of this worksheet is kind of seeing if you can make the next step, and it's actually what our notes are going to be about today. It's thinking, it's trying to stretch you a little bit. Okay, you've taken some notes on centripetal force, you kind of know the basics, you know the formulas, you've done a lab, but now what if it's going vertically? We talked a little bit about this in class, but now it's seeing if you can piece it together. And it's basically wanting you to see, they're basically testing, can you figure out, based on what you learned about elevators that were just going straight up and down, could you use that same sort of thinking and now apply it to something moving in a curvature? And so that's what the last page is stretching you for. We're going to talk about it and then we'll take some notes on it just to make sure you really get it and then give you some work time. So here, number 5, draw a free body diagram side view for a roller coaster on level track. Should the forces perpendicular to the track be balanced? If they are, explain why. This is a net force. Explain why there is a net force in the direction of the net force. Well, if the track is flat, is there any centripetal force? No. So the vertical forces should be balanced, right? I mean, this cart has no reason to change its direction. It should just keep going straight. So those forces should be balanced. There's no net force. Whether it's moving, whether it's sitting still, doesn't matter. If it's on flat ground, it's not changing direction, and if we're ignoring friction, then it's not speeding up or slowing down, so it's just balanced forces. And vertically, even if it was speeding up or slowing down, that'd only be horizontal. So vertically, they are balanced. All right, part B though, switches it. Okay, well now it's not level. Now we've got this roller coaster traveling over the top of a hill. So it's not just sitting on a hill, it says traveling over the top, so it's in movement. Which means it's not staying in a constant direction, it's actually changing its direction along that curve. If it's changing the direction of its velocity, that means there has to be what? An acceleration. If there's an acceleration, there has to be what causes acceleration?
Unbalanced forces.
Unbalanced forces or a net force. So there has to be a net force, there has to be an acceleration, which means these forces can't balance because there is a net force. Now, in the answer here, it says the forces perpendicular to each car are not balanced. Otherwise, it would go straight. The track has a curved path. The center of curvature of the track is below the car. Therefore, the car is accelerating downward. The circle shown, that dotted dashed line circle, sometimes known as a kissing circle, has its center below the car. So, seems like not a very physicsy word, a kissing circle, but that's what physicists call it. And the idea is that you can see the curve of the road. It's not really going in a full circle, but it's like part of a circle, so we can still use circular motion concepts. And if we just draw the part of that circle that matches it and have it kiss the road right where the object is, like just touch the road right in that spot, that's why they call it the kissing circle. We can do a few things. One, we can know the curvature, and therefore we can find the radius of that curvature. Because if we draw the circle, we just put a dot in the middle, find the radius. Secondly, we can visibly see that this curvature is below the car, which means the center of the circle is below the car. And if it is centripetal motion, what's the direction of the net force and acceleration? What's the direction of the acceleration and net force if it's centripetal? What does that word centripetal mean? To the center of the circle. So if the circle's below, the net force is pointing down to the center of that circle, which means its acceleration is down to the center of that circle. And so to be accelerating downward, the downward force of gravity, the weight of this cart, must be larger than the upward normal force of the track. Does this mean that the cart's weight changed? How do we find the weight of the cart? Yeah, MA or MG, right, where A is G. So would the mass of the cart change just because it's riding along? No. Does gravity of the earth change? No. So mg doesn't change, the weight doesn't change. So it's just a normal force that's different. If you're riding on this roller coaster and you go up over a hill, do you feel lighter or heavier at the top? Lighter, right? When you go up over a hill on a roller coaster at the top, you feel kind of lighter, like you're lifting off your seat a little bit. Did your weight change?
No.
No, but the normal force pushing against you feels less, right? You feel lighter. So that's what's going on here. The normal force is less, the seat's not pushing against you quite as hard, so you feel lighter, you feel like you're lifting off the seat a little bit, but your weight's still the same value it was before you went over the hill. All right, any questions about part A or B for this problem? Making sense how we can represent it with free body diagrams? All right, we'll scroll, oh, don't want to draw anymore, there we go. Scroll on down here to part C. Draw a free body diagram, again, side view for the roller coaster traveling through a valley. Should the forces perpendicular to the track be balanced? Is the cart moving along a part of a circle? Yes. So is its direction changing? Yes. So is there an acceleration? Yes. So is there a net force? Yes, right? All those things have to be true. It's like the chain of logic thought that you should go through. Okay. Well, if I draw the kissing circle, the curvature matches if I draw the circle above, right? That's where it fits into the curve. And if the circle is above, the center of the circle is above. And what direction does centripetal force always point? To the center of the circle. So the net force has to be pointing up since the center of the circle is above the cart in this problem. If the net force is above, the upward force has to be greater than the downward force. Yeah, Quinn?
Is the normal force the centripetal force?
We'll get to that later, but it's not the normal force, it's the net force that's centripetal.
Okay.
The normal force is how much the seat's pushing on you, but the centripetal force would be the difference between that and your weight.
Oh, okay.
Yeah. That's actually going to be part of our notes today, so you got a little preview. All right. So in this case, the normal force, you would feel heavier, right? As you go down through this valley, you feel kind of pressed into the seat, but your weight didn't change. You didn't get heavier. You just feel heavier, right? Your inertia wants you to keep going down, so the seat's pushing against you harder. The seat, another way to think about it, kind of going back to Quinn's question, the seat's bearing your weight and pushing you back to the center, right? So the part of it that's bearing your weight is just balanced out. But the extra part is what's pushing you back to the center. So it's the extra part that's the centripetal force. It's the difference between them, if that makes sense, right? Because it's doing both right there. It's supporting you and pushing you back. That's why it's greater. All right, any questions? Okay, we go to worksheet 1. Not a ton of math in that one, mostly just free body diagrams, but hopefully conceptually it helps you lay that foundation. All right, well, let's move on from there then.
What would you do?
No, yeah, I want you to keep it so you can use it as a study guide. All right, so now let's take some notes on that whole concept of vertical uniform circular motion. We're going to basically take what we just learned, kind of discussing worksheet 1 and processing that and adding some math to it. Before we dig into that, I just want to highlight the first thing we did on worksheet 1 with the car and the friction. That's the simplest kind of problem because the centripetal force is a single force. It is the friction. Okay, it is the friction in that scenario. Even, it's gone now, but I have it written over here. Even think about the gravity of the International Space Station. The centripetal force is the gravitational force, right? So those are kind of horizontal UCM, horizontal uniform circular motion kind of scenarios, where there is a force that's equal to the centripetal force, or also you could say equal to the net force. In vertical UCM, that's constantly changing, okay? Because while weight is constantly down, the tension and the normal or whatever it is is pulling at different angles. So it's a little more complicated with vertical to do the math. Not a lot, but just a little. And that's where it comes back to what Quinn was asking. We can't just say it's equal to a single force. It's actually going to be equal to the difference between some forces. Okay, so let's analyze this. Here is just a quick note if you didn't catch it from the worksheet, or if you just want to have it more in the notes. So if you're watching the video, if you look at these notes online, you see this reminder that no matter where the object is along a curved path, you can draw a kissing circle. You just make the circle match the curvature, and it should touch at that one spot, like the middle of where it's touching should be right on the object. So if the object is right here coming down the hill, the kissing circle would be there, the center is there, so the net force points to the center of the circle. So in the examples on the worksheet, it was right at the top or right at the bottom, but this is highlighting that it could be anywhere along the curvature. It doesn't have to be exactly at the top or exactly at the bottom of a hill or a valley. If it's this way though, here's the tricky part. Which way is the weight force? Straight down, right? Weight's always to the center of the earth. But the centripetal force is not straight up or down in this, right? It's at an angle. So whenever you have an angled force, what do you have to do? Break it into components, x and y, use the trig, right? And find the x and y components. And so then the weight force would be the y component of this centripetal, and the x would be a different thing we'd have to evaluate. So depending on the scenario, you'd have to use some trig if they didn't have it right at the top or right at the bottom.
But so going back to like the space station thing is like the velocity of the space station, the east vertical component is necessary for the gravity, and then it's like the other component is like what keeps it moving from home.
Yeah, so in these scenarios though, it's a little different. The mass won't always cancel out because in that case it was one force equals one force. But here mathematically it's going to be one force equals this minus this. And so unless mass is in all three terms, it won't cancel out. So if mass is only in one or two of the three terms, it won't cancel out entirely. So that's what makes this one just slightly more complicated. You don't necessarily have the flexibility like you do in those single, like this is this, like force A is equal to force B. Here it's going to be like force A is equal to C minus B. All right, you'll see it as we go through, I think, how that fits. So can I get someone to read this slide for us? Car on a hilly road. Don't be shy.
When a car goes through a dip, we can consider it to be in circular motion. Its acceleration is towards the center of the circle curvature, which is up in this case. We can use a free body diagram and Newton's second law to derive an equation for the normal force on the car. Since the acceleration is upward, the normal force must be greater than the weight force. And the net force is centripetal because it causes the car to move towards the center of the circle.
All right, so the logic there in red is kind of the key thinking, that we drew the kissing circle to match the curve. And so the center of the circle is above the car, which means the net force and acceleration have to be pointing up towards that center. And so since it's pointing up, the normal force must be greater here than the weight force. And if you think about your real life experience, if you're driving in a car and you go down through a valley like that, you feel pressed into the seat, right? Your weight didn't change, but it feels like it did, so the normal force just got bigger. The seat's pushing harder against you. It's bearing your weight and pushing you back to the center of the circle. So the net force, yeah, simply speaking, Newton's second law is just m times a. And sometimes that's helpful, but often it's just a starting point. In this case, we've got an upward force and a downward force. The normal force is bigger. The weight force is smaller. So if we just say the normal force minus the weight force, that is the net force. It's the difference between the two. It's what's left over when you cancel out what cancels out. So again, the seat's kind of doing double duty here. It's pushing you up, and it's in terms of bearing your weight, and it's also pushing you even harder to make you go along the curve instead of going in a straight line. So the net force is the difference between those two, and the net force is the centripetal force. So here's our equation, normal minus weight is equal to mv squared over r. So does the m cancel?
Yes.
Sure.
Well, can't you factor it out of the normal force?
Is the normal force just mg this time?
Oh, no.
It's not anymore, because now there's another factor. It's not balanced anymore. So normal force is not mg anymore. So we can't actually cancel the m, right?
So it's a different M?
Yeah, there's no way to calculate normal force directly with what's given here. We would
Oh,
have
okay.
to use it by, we'd have to find it by adding the mg to the other side and isolating it mathematically.
Okay.
Yeah, so we can't just say, oh, it's m times something else. I suppose if we could somehow find what the modified version of g was, we might be able to, but that would be harder than just using this equation and solving for it.
Okay, yeah.
Yeah. Like you could try to figure out, well, how many g's am I experiencing here, and then re-solve it that way, so that's possible, but it's a much harder step than this process. All right, so questions about that at the bottom of the valley? All right, and if you ever need to go back over and hear some of this again, I will be posting the video later today. These notes are also on Access, so you can also look at the notes. I think it's in PDF forms, because most of you wouldn't have access to the smart software. But you can look at the PDFs and kind of go over it again. You can watch the video if you need to. This is today's lesson. It's the end. Like, this is the last one for this unit. But we'll look at more examples in the future. But there's really nothing new after today. It's just various examples. So this is typically the one that causes the most confusion for students. So if you're still a little hazy afterwards, you can always look back at the notes that either that you took or look at them fully online or watch the video again. We get someone to read this second one here about the car on a hilly road. Chris?
When a car goes over a hill, we can also consider it to be in a circular motion. Its acceleration is towards the center of the circle, which is down. We can use a free body diagram and Newton's second law to derive an equation for the normal force on the car. Since the acceleration is down, the weight force must be greater than the normal force.
All right, so now we're at the top of a hill. So do we feel heavier or lighter?
Lighter.
We feel lighter. So the normal force must be less than the weight force. And we can also think it through mathematically. The kissing circle only fits that curve where it just touches the car underneath, which means the center of that circle is underneath, which means the net force points to the center of the circle being down now, and the acceleration points to the center of the circle, which is down. So the weight force, mg, must be larger than the normal force. So in this case, your weight's still the same, you didn't change, but your inertia is carrying you forward, trying to make you go in a straight line. So that fact gives the seat a little bit of a break, right? It doesn't have to bear your full weight anymore because your body's sort of lifting up based on its inertia. And so the normal force is a little bit less.
Yes, right.
Yeah.
Like, there'll be another circle as it comes downward, right?
Yeah, so we would only draw the circle at any one point in time. So if the question later asked about something here, you'd have to draw another circle and it'd be like a separate problem. Yeah. So you always just draw the circle where the object is at that instant and solve that. And then if it moves, it's like a separate problem almost. All right, any questions about that? Just the difference between being at the bottom versus being at the top. All right, so now let's actually solve one mathematically. So we've got a car traveling at 20 meters per second. The driver of the car has a mass of 60 kilograms. The car is located at the bottom of a dip in the road with a radius of 80 meters. What is the apparent weight of the driver? The apparent weight means the normal force supplied by the seat of the car. So whenever you see College Board use the phrase apparent weight, I've highlighted it in red here because what I added in the parentheses is not normally added by College Board. They usually don't tell you what apparent weight means. I've added that to make sure you're clear. So if they say apparent weight, what they're really saying is tell me the normal force. All right, and they're wanting you to tell them the apparent weight of the normal force when it's at the bottom of that dip. So I've highlighted those words in red, and then I've defined it in blue to make sure you know anytime they ask you for apparent weight, they're really saying, hey, what's the normal force? All right, so will this person feel heavier or lighter at the dip? Heavier, right? They're going to feel heavier. What is their actual weight? If they have a 60 kilogram mass, just using 10 for G, 600 newtons, just a rough estimation, right? 600 newtons is roughly their weight. So when we solve for the normal force, it should be higher than 600, right? The normal force, they feel heavier. The normal force is bigger than their actual weight. So let's prove that out. All right, so here's the sketch of the problem. What's the free body diagram look like? If the car is the dot, what are the forces? Normal force up, weight force down. How do they compare? What's that? Normal force is bigger? Good. Everybody following okay with that? Like what we looked at before, but here's the free body diagram. The circle's above, therefore the center of the circle's above, therefore the net force is upward, therefore the acceleration is upward, so the normal force has to be larger than the weight. Everybody okay with that step, just thinking through the free body diagram? All right, so how do I find the net force then?
mv squared divided by r minus mv.
So mv squared divided by r would be literally the centripetal force, right? Which is going to be the net force.
Yeah,
Yeah.
wait,
How do I find it just based on these two?
Minus, FN minus MG.
Normal minus weight, right? Normal's bigger, weight's smaller, so normal minus weight. And then that's going to equal the mv squared over r, because the net force is the centripetal. Now here's something, if you're still wrestling with this a bit, you may want to jot this in your notes. A lot of students think the centripetal force is the normal force. You have to really delineate between normal and net, all right? They are two different things. The net force is what causes it to go in a circle, which may be connected to the normal force, but not equivalent to the normal force, right? It's only a portion of the normal force that's actually doing that. Does that make sense? So it's the net force that is the centripetal force. And the net force would be the difference between those two. All right, so let's see that in action here. I only show you this slide just to highlight something that we mentioned earlier, but you can see here they've added a vertical y-axis and a horizontal x-axis with dashed lines just to give it clarity visually as to whether all the forces are on the x or on the y. In this case, they're all on the y-axis. And all they're really highlighting here is saying that because they're all on the y-axis, you don't have to do any trig. No components, no angled forces. It's a simpler scenario. I almost deleted this slide because it's sort of irrelevant for this question, in my opinion, but I think it's a good reminder that it won't necessarily always be all on the perpendicular or parallel, right? It might, like if the car was here, then we've got some angled forces and we would have to do the trig. Okay, so it's a good reminder that there are some scenarios where we would have to, but this one we don't really have to worry about it. All right, so the math. Let's look at it. We know the net force always is just ma, Newton's second law. That's kind of the standard where we start, but we can't stop there because that doesn't help us much in this problem. We know the net force is going to be the difference between those two forces. Normal's bigger, weight force is smaller, so normal force minus weight force is the net force. And we also know that because the object's traveling in a circular path, or at least part of a circle, its net force is centripetal in nature. So that net force is equal to mv squared over r. Now, the problem asks us to figure out the apparent weight of the person. So that's the normal force. We need to solve that for normal force. So we just add the weight, add the mg to both sides to isolate the normal force. And then I would have stopped here and just plugged in my numbers, personally. They went ahead and factored the mass out since it's in both terms. There's no real advantage to doing that in my opinion. There's nothing wrong with doing it either, but I don't see how it helps. It's like one more step and it saves you typing in the 60 kilograms twice, but you had to rewrite that whole step to do it. So I don't think it really saves you any time. So I would have probably just plugged in my numbers at the step right above that, but you can see how they did it here. Plugged in the mass, plugged in 9.8 for G, plugged in the 20 meters per second, which was given for the velocity, plugged in the 80 meters for the radius, and the person feels like they're almost 900 newtons when they're really only 600, right? We said earlier they're 600 newtons about, and now we found out they feel like they're 900 down at the bottom of this dip. The seat's pushing back. So if we use that 600, 900, what's the net force? If their actual weight is 600, but the normal force is 900, what's the net? 300. So the centripetal force, if the question had said what's the centripetal force, the answer would be 300. It's the difference between the two. Because the seat has to carry the 600 weight and provide 300 more to push them back into the circle. That's basically what the math is telling us. Okay, if we use 600 and 900 instead of 888. So 600 to bear the weight, 300 more to push them back and make them going along the curve instead of in a straight line. That's what the numbers break down to. Any questions on how this math pieced together at all? All right, anybody need more time to jot anything down here? I don't want to rush you. All right, the next slide is just a quick summary of everything that this problem helped us process. And that's it for the day. So on the flat road, so if this is a hilly road, when they're on flat surface, the normal force and the weight force would be equal and the seat would just be bearing that 600, or if you use 9.8, it's 590, right? And then on the bottom of the dip, we found out it's closer to 900, 888. So the difference between them is the centripetal force. It's how much the seat has to add in to actually make them curve back into the circle and not just go straight. The gravitational force on the driver, mg, doesn't change. The weight of the driver doesn't change at the top of the hill, bottom of the hill, side of the hill. That doesn't change. It's just the normal force that changes. All right, that's it for the notes today. Couple of examples of uniform circular motion in a vertical kind of a setting. We'll look at some other examples next week. Any questions on this today before we switch gears? All right, so the last bit, we got about a half an hour left. I want to give you some time to work with your groups on the lab, but I want to give you a couple pointers first of all. As you're breaking down your data and you're trying to figure out whether it's quadratic or linear, or is it square root quadratic, or is it traditional quadratic, am I squaring the x, squaring the y? On your intro to UCM worksheet, all those equations are listed right across the top, right? If you look at those equations, it might help you sort of predict, oh wait, that looks like that might be quadratic. That looks like maybe we should square this value. Maybe we should square that value. Oh, that looks linear. If you look at those equations, it can kind of help you predict, because I can guarantee that none of you are going to have pristine data where your R squared values are going to be like 0.999, okay? If you get 0.9, you're doing pretty good. If you get 0.999, you probably cheated, because this lab is really hard to get excellent data because of the friction and the angle of the stopper and human error on reaction time, and there's a lot of error built into this experiment. So if you're getting a 0.9 R squared value, you actually did probably pretty good. So be satisfied with that. Realize there's going to be some outliers in your data, and look at those equations to see if that helps you piece together, oh, I think this should be quadratic. Let's test that. And what you'll find is sometimes the linear and the quadratic give you almost the same R squared value because the data is not terrific. Okay, it's just the reality of it. But it also doesn't tell you, So basically it's saying one is probably as good as the other, so then choose the one that makes sense according to the equations we've learned. Okay, so that's your hint. Here's a couple of pointers here. How many of you in this class actually did change the different stoppers? A couple of groups, okay. So if you did that, you have your own data and you're good to go. And I would like to get like one representative from each of those groups to come up and type your data in real quick for me, so that other groups can get it. If you didn't get that data, I've created a spreadsheet. And I've already shared, this is the data from my section 1 class. So there were 3 groups. So there's 3 groups over here on the left. And we got 2 or 3 groups. We'll add your data in here. And then I've already put this version of the spreadsheet on Access. So you can look at it on Access, or you can even download it as an Excel file and take a look at it so you'll have your data. What you don't want to do is look at all of them. Just pick one. I wouldn't probably choose this group because they only got 4 data points. Okay, so that's not terrible. At least they got something, but the other 2 groups got 5 data points and 5. Michelle, you said your group got some. How many did you guys get?
I think we got like 3.
Okay, so
4.
if you only got 3 or 4, we'll go ahead and put it in. But yeah, you even may want to, your group, choose one that's got more, because the more data points, the clearer you can see the shape of the curve. And then somebody else, Quinn, you said your group. How many data points did you guys get?
I need to find.
Find it. Anybody else in your group remember how many
It's like
stoppers?
6 or 7.
6 or 7. Okay, that's great. So you guys may want to use the data from that group because they got quite a bit of data points. All right, so we'll have both groups put their data in here, and then I'll update what's on Access. But for those of you putting your data in here, I put formulas. So once you type in your data, it's going to calculate frequency, speed, acceleration, and force for you, so you can check your work to make sure you're on the right track.
Oh,
You got
it is
5?
listed. Oh,
Okay, still 5 is reasonable. We've got the best we have so far is 5. So, and then what you have to do in this 30 minutes: work with your group, think through the labs, report, think through the graphs, share your data. And I do need those 2 groups to come up and put your material, your information here on the spreadsheet. I'll put this back up on the screen for you and just kind of freeze that there. This is just a reminder. Don't forget that while this red part, you may not have your own data, you still have to get data from one of the groups to do this part. Okay, so this red part's not optional. The only thing that's optional is that one graph. It is bonus points though. So since it was on the rubric, I went ahead and added it back to this slide. And if you choose to do that radius versus centripetal acceleration, you can get up to 3 bonus points for graphing it and showing the relationship. Okay, so it's optional, but the red part is not optional. All right, Michelle, we can have someone from your group put the data in as soon as you get organized, and same thing, Quinn, if you, one of you can put the data in here. Yeah, just go ahead and type it in. Let's have you put it like this, starting in that cell there.
Toga and more.
Oh.
Oh, okay. I was like looking at that, I'm like, what in the world is that? Okay, that makes sense.
Yeah, just don't type in the whole thing every time.
How should we get the
I'm gonna
data
go
for this? Like, should we just go with the copy down?
Or it's on Access, and you have to read it, or you can wait until I get it in, and then you can copy it down here too, either way.
I'll put it on there, hold on.
I used to buy
So we can just grab whatever groups. Those are just gonna be like.
Yeah, just pick a group that's got, 5 data points, rather than the ones that have less, but.
Dang.
Yeah.
Oh, and you have on.
Okay, this is the tension force of things, okay.
But like when I.
Okay, go back to the table real quick, and let me check something. I think it said you have some undefined values.
You know, Griffin's like the #1 post player. This kid's going crazy. He's gonna need like 2 goals.
Oh,
He made more goals than
there's no
Velocity, I
data
guess.
point here.
Yeah. Probably 3.
If you have empty cells or undefined cells, then it's gonna give you an error.
I mean, you wouldn't get anything, because all of it is the.
So I don't know, maybe the zeros need to be deleted, I'm not sure why they're there.
I don't think there was anything.
Alright.
Yeah, so just get rid of the 0, otherwise it's looking for another data point.
relatively consistent.
We just need to find one that's
That probably will fix it for you.
No, no, no one has.
Oh, wait.
You do need to put in the tension and radius so it can do the rest of the calculations.
Yeah.
Should be constant, but
Yeah, radius is 40 centimeters, so that's.
That's good, except for the fact that the period kind of like caps right here, that's a little weird.
Well,
This one's, never mind, this one's really inconsistent.
oh, choose that one.
This one?
Choose
and
that
then
one.
your tension force should have been constant too,
No, the
but
one
it
that
needs it
was-
in there.
Yeah, this one.
200 grams, so that's 0.2 kilograms. And then
So
times.
So on the graph.
I use 9.8, so.
Also, I typed in
0.2
the
times.
tangential velocity and centrifugal.
Yeah, that's all
Or wait,
that,
did I type in
Yeah, one
centrifugal?
you didn't do centrifugal for,
96.
Oh, yeah, I did.
you did for
I
this
did-
one.
I did the other one.
You're good, you're good.
I think for the first one with the mass change, it's gonna be linear because
Okay.
the
Is
centrifugal
that it?
force has
Yep,
to
that
match
should be
the
it.
tension force.
Alright, so if you guys wanna type your data here in
Or like,
this grid,
And so, m times the.
Wait, so does the mass of the hanging actually matter in this situation?
That's a constant,
Okay, so they didn't put that.
yeah, it doesn't matter.
do you guys want
Okay,
to
so
share, I have a
change this to
cable you
tension
can connect and he can share this file, so.
Oh, I have like pictures of it.
Oh, okay. Yeah.
You good?
Is this
I'll update it.
This one's.
Right now, what's on there just had the first periods, but after you guys get yours in, I'll update it so it has everybody's.
Okay.
Oh, damn, you know my back, it's like, it's really weird, I've been having back issues for whenever I come off of anything. It's just a constant strain, and it's been happening for like, right before I stopped working out, it like started happening really badly, which is why it's really hard to get back
Oh,
into everything.
what tension force, like, what's the weight of bulb we use for?
I just
Like I said, oh, 50?
Oh, the constant.
I think, was it 50 or 500?
Oh, wait, that was definitely like.
Oh, yeah, it should be 500.
0.35.
Was it 500?
I think so.
0.44.
So,
No, 500. It was 0.5.
0.5 times 9.8.
Observations on the, do we need frequency?
And then.
No.
We just need to do a bunch of calculations.
No, you just said that's like an option that we should consider. Or the observation section.
Oh, yeah.
Which is the velocity.
Our radius data is
It's
actually, we got 0.8.
So.
Yeah,
Well, he said that like
0.9 is.
0.9 is like
That, we got.
impossible.
We got 0.9
I
on
guess.
the first, on like the tension The radius one
They
is
didn't even
not.
have tangential velocity, they just have, oh wait, that's his speed.
Oh, wait.
I'm so dumb. We don't talk about that,
I
they
can
didn't have it, okay?
divide by 10.
Mr. Webb,
And then I put this in for you.
I didn't divide by 10 for the seconds.
What's
Because we
that?
did 10 revolutions.
I thought the first.
Oh, okay.
So that's like,
Wait,
Alright, so your periods are all, let me just fix that.
yeah.
Okay, I just did it for you, so just all decimal is different.
Is the one,
Yeah.
velocity versus,
So